from classical particles to classical fields. Here's what we're going to talk about today. We're going to talk about what is, in parentheses, quantum field theory. What is it good for? I'll do a brief review of classical and quantum fluctuations. It's a word I threw out last time, and it's a word of the physicist that should be intuitive to you as a physicist. I'll briefly review correlation length, the physics of it, and I'll review the topic of last lecture from classical to quantum, from classical particles to classical fields. And then finally, I'll end with a punchline, which is basic principles of statistical field theory. All right. I'm assuming you're going to ask questions whenever something is unclear. So what I do, if those of you guys have taken courses with me, is that every lecture I start with a summary of the previous lecture. So this time, that summary is going to be the whole thing. That's basically the way it works. Particles versus fields. So let's start where we all agree. Electromagnetism. You guys have learned about ENM, electromagnetism. And so the classical formalism that you're familiar with is in terms of a bunch of fields. What are fields? These are vector fields. These are vectors defined at every point in space-time. Electric and magnetic field, we often package it in a covariant form as the vector potential, which is a function of space-time with four components. So an electromagnetic wave is a field, right? For example, a wave propagating down from the sun to the earth, that's a field. But you know, or you've heard that the same physics could be described using particles, a traveling photon. So there's a photon that leaves the surface of the sun, spends 8 minutes and 20 seconds, it gets to the surface of the earth. It's describing the same physics. All right. That's classical. So classically, it seems like they are equivalent formulations. Quantum mechanically, you also have learned about some sort of a interplay between the two, the so-called particle-wave duality. So in quantum mechanics, you've learned that this example above does not just apply to photons, it applies to all particles. Every particle could also be viewed as a wave. The same way they could think of a phenomenon as an electron moving in space, you could think of it, describe it as a wave, electron wave in space. And this wave is going to be the foundation of, it's a field. It's a function of the space-time, right? You already can see here, whatever is that wave, to be called a wave, a particle, you have a bunch of requirements. What are those requirements? Localized excitation carries energy, right? Localized means that it could move it around, right? It can move with constant velocity. It has an approximately well-defined location and velocity, right? That's what the particle is, or at least some of the properties of the particle. All right. So just naively at this level, this suggests that we will not be able to do physics. You have used two different frameworks to describe the same physics. Okay. What is field theory? Field theory is a theoretical framework for many-body physics. That is a very important term here. It doesn't make sense to talk about field theory for a single-body system. Well, it does make sense, but in a trivial way. It's a theoretical framework for many-body physics, from very high energies to very low energies. So whoever told you that quantum field theory is only relevant at very high energies, they're lying to you. Where the fundamental particles are fields. Fundamental objects, building blocks, fundamental building blocks are fields, functions of space-time. In this picture, particles are emergent. We will argue today and the next lecture that fields are more fundamental than particles, both in high energy and in low energies. In fact, I suggest that you read up on this. not all many-body theories, not all field theories have particles. Some of the points that I make here, I'll argue for along in the middle of the lecture, but I might not point out this argument implies that. So that's for you to fill in the picture, right? Fill in the gaps. In quantum field theory, we quantize these fields. All right. We said this before. What is quantum field theory good for? Quantum field theory is good for different sets of problems that I can think of right now. One is that it describes classical finite temperature quantum many-body systems near a continuous phase transition. I'll explain what that means, or at least give you some intuition about that. So this is going to be this part. Classical or quantum, and quantum, right? Quantum field theory, when we're talking about the classical finite temperature system, we often call it statistical field theory, but it's the same framework, up to an extra I. That's the I that those quantum finance people just like. Quantum field theory is well defined at zero temperature at arbitrary temperatures, whereas statistical field theory is finite temperature physics, classical physics. Okay, there's something. If you're curious, there's something called the classical quantum correspondence between a finite temperature classical system and a zero temperature quantum system. You could read up on that. All right. Quantum field theory also combines special relativity, same formula that could use to combine special relativity and quantum mechanics, and it leads to a whole set of a beautiful theory that describes all particles we've observed in nature, except for graviton, and their interactions. And we have them observed gravitons. I couldn't have said that 10 years ago, but now we have observed it. This is the so-called Standard particle physics. This is going to be the holy grail where we're going to work this whole year towards. We'll end on defining what standard model is and proving that it's a consistent quantum field theory. That will be the punchline of year 2. And also, attempts to combine general relativity and quantum mechanics have been successful in a particular setup. And those theories have a shocking result that came out of this success story was that these theories of quantum gravity were secretly quantum field theories in lower dimensions. This is a so-called holography. All right, so this is just motivational. All right, so I'm taking a step back. I'm reviewing very, very quickly some facts about statistical physics. So the goal of the next few slides is to give you an intuition about what thermal fluctuations are. And everything I write on these slides, the next few slides, the index I is a particle index that runs from 1 to 17. The finite number of particles. All right. So what is a microstate in finite temperature classical particle physics or statistical particle physics? It's a definite set of Qi's and pi i's. Each Qi pi I is a point. Each pair is a point on the phase space of the I particle. Why do I say this? Why do I focus on this data? Because it's sufficient. If you have that data, you could evolve the equations of motion and you know the future, predict the future of these particles, right? So that's what a microstate is, a point on the phase space. Good. What's a Hamiltonian? It's a real function of microstates. So every microstate attaches a positive, well, not necessarily positive, a real number called the energy. So it's a function. Now, in the statistical physics, the word is statistical. It means that you're not dealing with a particular microstate, but what you have is a state. What is a state? It's a probability distribution over microstates. Good. So it's a probability distribution on the phase space. Good. As a physicist, you should take that as the very definition of a state. Instead, and what's the origin of this? So thermal physics is one way to motivate this. To say that when you have a gas of particles, right? This system interacts with the bath through its walls, and you would never know exactly what microstate the system is in, your best description is the probability distribution over microstates. So you don't, instead of a definite microstate, you have a probability distribution over them. P of Qi pi i's. Now you see why I use pi and not P for momentum. Yeah.
A general basic question. Is it possible in this formalism to know the exact energy of a state then? Or is
State means microstate?
State meaning state.
So what does it mean to, okay, I'll get there. If the next slide doesn't answer your question. All right, so a state is a probability distribution. What is a finite temperature state? A finite temperature state, aka Gibbs state, is the following thing: when the probability of a configuration is proportional to e to minus beta Hamiltonian of that configuration, energy of that configuration. That's the very definition of a finite temperature physics. What's finite temperature physics? It's a particular state somebody wrote down and called it Gibbs state and gave it to you. They said, this is your state. All right? So let me elaborate a little bit more. This H is an energy of a configuration. Beta is a positive number. It's interpreted as inverse temperature. What's the dimensionality of beta? 1 over energy, otherwise known as length. Right? Now, if the Hamiltonian, so Hamiltonian is a function of the phase space. Hamiltonian has units of energy. Whatever you put in an exponent better be dimensionless, right? So you should be careful with your dimensionalities. If your Hamiltonian is dimensionless, that means that you have eaten the dimensionality of that into beta. Okay? Typically what happens is that in the models that we're going to describe, there will be a lattice scaling, some fundamental scale, right? That you could introduce in there, right? So for example, if there's fundamental lattice scale epsilon, your beta, which was dimension full, had dimension of length. The dimensionless parameter would be beta over epsilon. And epsilon h would be dimensionless Hamiltonian. All right, what is this z? Z is the partition function. It's the normalization of a probability. When you say the probability is proportional to that, the fact that probabilities have to add up to 1 tells you that if you sum all of them and divide down here, you're going to get a probability distribution. What is that? So that's a partition function. It's the sum over all microstates of this Gibbs weight. So what the setup to this states associates the probability distribution to the particles moving in like this, particles that move this way. This could be addressed. As a matter of fact, this is a Gibbs state, but you could come up with something called grand canonical ensemble, where the particle number is not conserved. So this picture, the system exchanges energy with the bath. So there's a probability to find the microstates of different energy, right? But you could also have a setup where your system exchanges particles with the bath, right? What's that called? Grand canonical. Yeah, but what's the analog of beta over there? All right.
There's a beta and a mu.
Yeah, what's mu? Yeah, it's a chemical potential. All right, so now what are observables? Observables are real functions, real smooth functions on the phase space. Q or pi is something you can observe for particle I. Qi is something you can observe, pi is something you can observe. Qi squared, Qi pi j, these are all things you can observe. Now, to come to your question, the fact that instead of in a microstate, we ask the question of what is the value of Q1 pi 15? When you have a probability distribution, the only meaningful thing this is a random variable. The only meaningful thing to say is, what is this expectation value? Or what is this fluctuations? Variance, right? Higher moments. What are the moments of it? What are these moments called in physics? Correlation functions. Thermal correlation functions. So what are fluctuations? The fact that you have a probability distribution, it means that to a state you could not attach a definite value for observables. Instead, what you associate to each observable is correlation functions. What you talk about are correlation functions, right? For example, the thermal expectation value, this is of this observable QJI J1 to Jn pi L1 to Lm is sum over all microstates, the probability of each microstate, the value of the observable in that microstate. Right? This is the expectation value. All right. Let's say what the hell is fluctuation? Fluctuation is just the fact that you have a statistical, these are random variables. But to make it very clear, let's look at the simplest example possible, a 2-point function of Q's, Q1 and Q2. If these guys had, if you had a single microstate, right? Then if you took the Q1 and subtracted from it its expectation value, right? That will be a trivial thing. The expectation value, thermal expectation, this is called fluctuation. So an observable, so this is an observable. Its expectation is on average, it takes a particular value. When it fluctuates, what it has like different fluctuations from this, you subtract from it is expectation value, right? This, the fact that this has moments is that this fluctuates, this variable fluctuates, right? So let's look at the expectation value of the second moment of this. Just expand it. You've learned that this is the 2-point function of Q1, Q2 minus the 1-point function of Q1 times the 1-point function of Q2. This is called the connected correlator. Each of the first term is a correlator. Each of these are correlators. This is a connected correlator where we've subtracted the disconnected piece. We're going to describe that. But I'm just throwing you, or 1-point function removed. When you have fluctuations, this is non-zero. Good? So these are thermal fluctuations. The origin of it is the fact that you have your state is not a definite microstate, it's a probability distribution. For example, in finite temperature physics. Now, the partition function is the master function, it's the generating function for all correlation functions. Define the partition function with sources ji and ji tildes. So what is that? It's just, so what was the partition function without sources? It was just sum over all microstates of e to minus beta energy of the microstate. Add to it a term, which is jiqi, sum over i's, right? That's implied. Repeated indices in this course are summed over. Let's just say that. Plus ji tilde pi I tilde. These are called sources. Just define this object. All right? If you calculate this and take derivative with respect to some particular j, set that j to 0, what you find is this is just a 1-point function of qj. It's a method for calculating correlates. That, once you know that the source partition function with sources, this is an elegant way of repackaging all correlators. Right? Now that's 1-point function. Here is an arbitrary point function. You just take derivatives first, then you set the sources to 0. Questions? So let me actually read this punchline and then stop. Ask for questions. So in summary, thermal fluctuations lead to uncertainty or variance in the position and momenta of particles as they interact with the bath. The moments of the observables are correlation functions of classical many-body finite temperature physics. Everyone's with me? All right, so that's what thermal, every time in this course I said, or for the rest of your life, everyone said thermal fluctuation, that's what they mean. Questions? Yeah.
I missed what you said J was, in this case, I don't think generator.
It's a trick.
It's just like a placeholder for Q or?
No. It's a, you're asking what's the physics of it or mathematics of it?
The mathematics.
So the mathematics of it is that I just defined this new object that is the partition function if I said j and j tilde is equal to 0. But when they're non-zero, it's something else. It's a partition function in the presence of sources. It's a method. There's some physics associated with it. It's like turning on a background field. But we're going to discuss this. We're going to beat this up so much that it will become intuitive to you guys. But for now, it's just an elegant way of packaging all the correlation functions in one function. Right? Questions? All right, so what did I explain so far? I explained what the state, what the thermal state is, what the statistical finite particle physics looks like, and what correlation functions are, and what I mean when I say thermal fluctuations. Now let's go from classical particles to classical fields. So this is, I'm just describing to you what classical field theory is in 0 plus 1 dimensions. First, I'll do it. Well, sorry, let's call this D plus 1. Okay, one of the things that I'll do in this course, I apologize in advance. I have to go back and see my notes. Every year I teach, I use a different signature for the metric, and also I use a different D means sometimes space dimension, sometimes means space time. I'll try to be consistent once we get to relativistic setup. For now, D is the dimension of space, right? All right, so let's think about classical single particles. Sorry, not single. Finite number of particles in D spatial dimensions. All right, what are the degrees of freedom? Why is this D? Say I have, how many particles should I have? 17. So classical 17 particles and D dimensions. Okay. These are the degrees of freedom. The Hamiltonian is a function here, and you have a. Okay, good. No. Sorry. I messed it up. Sorry. I said something completely wrong. Yeah. Consider a single particle in D dimensions. My bad. Right? Now the position, this QI is a different thing, right? This is like, maybe I should just use this language. I think this is a better language. Q and pi. Right? Now, each of these guys have D variables because they're in D dimensions. Hamiltonian is a function of this. Sorry about that. All right. How do you contrast that with field theory, classical field theory? In classical field theory, the degrees of freedom are fields in space-time, right? And there will be a conjugate variable associated to each degree of freedom. And then the Hamiltonian is just some function of the field and its conjugate momentum. Now, if your field theory is in 0 plus 1 dimensions, your fields are functions of only time, right? Let me just put these guys also. These are functions of time. Right? So it looks like that, no, it doesn't look like. It's a fair comparison to see a single particle in these spatial dimensions is D copies of classical fields in 0 plus 1 dimensions. Good? The next step I'm going to take is something that is a level of abstraction. It's a little bit abstract, but it's very familiar to you as physicists. When you talk about classical particles, classical degrees of freedom, it doesn't always have to be position and momentum. It could be what we call in classical physics generalized coordinates. There you have a pendulum of length L, angle theta. This is just somewhere at some fixed point in space-time. And your dynamic degree of freedom, classical degree of freedom, is this theta. Of course, let's give this guy a name. We're going to call this a rotor. All right? There is the degree of freedom, classical degree of freedom is theta. There will be a conjugate momentum, P of theta. There will be a Hamiltonian associated with it, which is this. Cosine theta was correct on the previous slide, last class. So this is what it looks like. The Hamiltonian has a kinetic term and has a potential term. Good. All right. So this is also a single particle. Single classical degree of freedom. We're going to call this a rotor. Why do I call it a rotor? Because I want to generalize it. Now, here's the punchline. This whole QFT1 course, we're going to end with one sensible theory of quantum field theory. That's going to be a rotor model. It's called the ON model, right? And it will be the only model we could achieve by the end of this course class, this semester. This is going to be the holy grail. It's the only thing that makes sense. We'll do a lot of like ugly subtraction, addition of infinities, nonsense, but this will make sense. All right, so it's important that you remember this. What is this? This is the degree of freedom, the rotor model, if in of this pendulum, 2D pendulum I was drawing. So I can think of this as some vector, 2D vector of length L, with x and y coordinates L sine theta, L cosine theta. More generally, a rotor is the degree of freedom that is an n-dimensional vector of fixed length. Let's call it unit length, setting L equal 1. So it's just an n-dimensional vector that has unit length. Let's go through examples. If it's a one-dimensional vector of unit length, what is it? It's a spin degree of freedom. It's either +1 or -1. It's a classical Ising spin, single degree of freedom. N equal 2, it's an XY rotor. I'm not writing a Hamiltonian yet. I'm just talking about degree of freedom. Right? This can rotate. So it's just a vector. I can draw it this way. Right? If n equal to 3, this is a Heisenberg rotor. We're going to call it a Heisenberg. It's just like something in 3 dimensions. You could easily imagine this for general n. What we're going to do is so for the Ising spin, sorry, good. You're with me? Now that I know what this class of rotors are as a single degree of freedom, I could take a lattice, arbitrary dimensions, and put one of them on each side of the lattice to define a many body version. So for example, I can have many rotors, each sitting at a point on line. To make it look a little bit more familiar, I can draw it this way if these are Heisenberg rotors. If they are Ising rotors, what does it look like? It looks like an Ising model, 1D Ising model, right? You just put it on a lattice. What makes it? So this is so far, I'm just defining the degrees of freedom. Physics starts with the Hamiltonian. Once you fix a Hamiltonian. What is the Hamiltonian I'm going to pick? I'm going to pick on this 1D lattice, I'm going to pick a nearest neighbor Hamiltonian for the XY model. More generally, on an arbitrary lattice, what's a good choice? Nearest neighbor Hamiltonian, right? So we write the sum over ij of Si, say Sj, minus some coupling. These are only summed over nearest neighbors. What is, as a physicist, you study this Hamiltonian, and what's the most important feature of it?
What minimizes it?
No. Just when I wrote this, what was the most important essential ingredient? Locality. For things to talk, they have to be sitting right next to each other. Right? This is locality. So we're going to pick a local Hamiltonian like this. All right? In vacuum, what's the vacuum of this model? XY model in 1D? As twofold degenerate, either all up or all down. Oh, sorry, no, sorry, wrong, incorrect. What's the correct statement?
Well, it depends on if J is positive.
I said XY model, right? What's the energy of this? So what did I write? I wrote minus J sum over I SI dot SI plus 1, right? What is the dot of these two guys? Each pair, adjacent pair.
1.
1, right? This is minus, and that's the largest thing it can be. Therefore, this is maximally smallest value possible, right? What if I take this, and what about this state? What's the energy of this guy? Same. So it's now twofold degenerate, right? It's degenerate if you take any state and rotate all of them with an orthogonal rotation, right? The energy is unchanged. What are such transformations? For all SI, you're going to multiply it with the same ON matrix, right? What makes it ON? The fact that this holds, which means that this is an ON matrix. Just a rotation. Sorry, ON, O2. My bad. This is the first appearance of two key ideas in writing the Hamiltonian down. First, locality. Second, it has a nice symmetry. Symmetry and locality. So as we said before, once you're at high temperature, there are thermal fluctuations, and all states contribute with a Boltzmann probability like this. So here is the ON model. The ON model is, I already wrote it. You put it on your favorite lattice, arbitrary dimensional lattice. The degrees of freedom are vectors on, so think of it this way. Here's a lattice. Okay. On each point, there is an imaginary Sn sphere, n-dimensional sphere, and the degree of freedom is a vector here. So there's one over there. There's one over here. There's one over here. This picture will be coming back over and over and over again. This is perhaps one of the only ways we know how to define a sensible field. You put a rotor at each point on the lattice. Good? Questions? Oh, sorry, I forgot to say. So for n equal 1, this model is called Ising model. For n equal 2 is called the XY model. For n equal 3 is called Heisenberg model. For general n is ON model. You might have heard about the insane success of the Ising model in describing statistical models. This is a huge generalization of it, and it's been incredibly successful. So much that most of today's field theory is about these points. Even the fancier models we come up with, you're always guided by these two principles, locality and symmetry. By the end of course this year, those of you guys who continue QFT2, you will learn why we want symmetry. Nobody says you must have symmetry, but symmetry helps us ensure the theory is healthy. We'll get there. Yeah.
Is the J here just an arbitrary constant?
Yes. I'm taking it to be positive. Doesn't really matter. It actually does matter. Take it to be positive. All right. Questions? It's all classical physics so far, thermal fluctuations. Now, I said this before. These are rotors. Are rotors particles? I don't know. It depends. The word particle is what depends how you want to call things. But if you look at the vacuum of this theory, let's take Ising model for simplicity. The vacuum of Ising model in 1D is twofold degenerate, all up or all down. Right? Because O1 is Z2. It's a silly thing to say. Now, what are particles? What are things that look like particles? What do you expect from particles? These are local excitations, right? That could be moved around. So one natural thing to do is, well, if you just take half of these guys up and half of them down, this is an excited state. And it has a little bit of a kink here. Something has gone crazy here, right? This is let's call it a quasi-particle. We can also move this around. It costs no energy. The same way that you could move if your whole world is a single particle and move it around, right? Costs no energy. You could just move this around. You could give it momentum. You could kick it. You could write down a solution where this kink, right, moves down the constant velocity, right? So is it a particle? Let's call it quasi-particle for now. But a funky property that's obvious at this point is that now there are particles and there are other types of particles. So the up-down one is one, the other one is down-up, and they can annihilate, right? If you send them down, collide them, right? If you bring one from infinity here and the other one from here, make them collide, they will just annihilate. So whatever this quasi-particle is, the particle number is not conserved or something funkier is going on. Maybe these are different types of particles. Maybe this is an anti-particle, anti-quasi-particle. We'll have to decide. But it looks like the notion of particle is just some sort of a localized excitation that just moves in space. I'm going to have to characterize it a little bit more to sharpen this. Questions? How am I doing on time? All right, I'm doing well. It's on till 2:45, right? I'm going to change gears, so it's a good time to ask questions.
The obvious, really suggestive question is, if you send two of these quasi-particles into infinity, collide when they annihilate, what happens to the energy that they carry?
Very good question. What happens? Yeah. There are lots of interesting questions to ask. Right. All right, but this is an analogy, right? I don't literally mean, I just wanted to say that, hey, the notion of a particle, quasi-particle is kind of like malleable. It depends. What you kind of abstract out from it is it's a sort of a local excitation that could be moved around freely. You could create a bunch of them if they are far apart, right? And their energy hopefully just adds up. The energy of two of them is equal twice the energy of single particles if they're really, really far away. All right. Next, what I want to do is I want to remind you guys what the notion of correlation length is. And it's not just a mathematical definition. I'm going to give you intuition, hopefully, as how to think about this, because it's one of the most fundamental intuitions you should have as physicists. All right, so let's take the Ising model or the ON model. I'm just going to write it this way. Let's look at the 2-point fluctuation. All right, aka connect the 2-point function. So in the notes, I'll have all sorts of, I write statements and say, show, argue, this is for you. You could consider it homework problem, additional homework problem. But as I said earlier, the course is for you. So I think you should be spending time thinking about these questions if you want to be able to follow. So for the Ising model, first, using translational invariance of Hamiltonian, the Hamiltonian has another symmetry, translation invariance, right? Show that this guy is only a function of L. Oh, sorry, this is a 2-point function. This separated by L, two sides separated by L. So this is S1, S18, 20. So that we can choose it together. So. All right. So this is that 2-point function. Translation invariance means that just write, I don't know, 10 to the power of 17. That's my favorite number today. Is independent of that 10 to the power of 17. Right? What is L? L is this 28. It's the difference, the distance between them. I'm calling it L. And it's dimensionless. It's just an integer, positive integer in this notation, right? And then you have beta, which is also a dimensionless positive number. Good? So first argue that this guy has to be a function of only L and beta. At least at large L. Then argue that this connected correlator has to go to 0 as you separate these guys infinitely. All right, this is called the clustering principle. What does it mean? Can anyone explain this to me? Yeah, can anyone explain this to me? What does it mean for the correlator? Yeah, go ahead.
Well, that correlator goes to 0, meaning, what's going on at one thing is kind of completely independent of what's going on at other things when they're very, very far apart. But as you get closer, as L gets far from infinity and smaller,
Yeah.
that correlator doesn't go to 0, eventually becomes large, and then these things are all doing something that is interrelated. So connected behavior happens in these sort of local clusters.
Right, but the principle is that as you things that are very, very far apart are independent degrees of freedom. Good? This is an intuition you share, but you should be able to argue. Now, can anyone explain to me what independence means? It's my next. Oh, no, actually, I have one more thing. All right, let's go through this and then we'll describe what it means. So it goes to 0. The connected part of the correlate goes to 0. But if a function falls to 0, how does it fall to 0? What kind of functions falls? Well, we're physicists, right? Tell me some functions that decay. What are the things you could write down? They're pretty much, as physicists, like these are the only things we would write down. Non-mathematicians, which are very different. Exponential, it could decay exponentially fast. If it decays exponentially fast, L is a dimension full parameter. Let's say lattice spacing is epsilon, so I'm talking about L epsilon. So there's an exponent that sits there. We're going to call that correlation length. It's a function of beta, right? Every time you are dealing with a system that shows exponential decay of connected correlators, we're going to give those systems a name. We're going to call them gap systems. This is mostly quantum terminology, but I want you to get used to it slowly. We're going to call it gap systems. The other thing that it could, so the exponent requires a length scale. Can you write down something that decays away to 0 without introducing a length scale? There's only one way to do it. Just write 1 over L to the power of some power law, positive delta. Right? That's parallel behavior. We're going to call that gap less. This behavior is seen at criticality in continuous phase transitions. This is, if you wish, it's a definition. I could take it as a definition. If a quantum system, statistical system, classical fine temperature physics, many body, shows 2-point functions, connected 2-point functions that decay away to 0 at some critical temperature as 1 over distance to the parallel, we say you're at a continuous phase transition. Right? Notice that this way of defining things, I didn't even mention Hamiltonian. There's a beautiful line of thought these days to talk about, do you even need to talk about Hamiltonians if you want to classify phases? I personally believe you don't. But anyway. Good. This is purely in terms of the state, right? I'm not talking about Hamiltonians, right? Just the state. Well, the Hamiltonian is hidden in the thermal state, but anyway. Now, the more general thing that's possible is that what you have is the parallel sitting next to an exponential decay. This is the kind of behavior you see as you have when you have a critical system and you tune your temperature near criticality. So your temperature is close to some phase transition. This is how the correlator behaves. From this, it should be clear that another way of talking about continuous phase transitions is the system undergoes a continuous phase transition if the correlation length goes to infinity as it tunes the temperature to the critical temperature. Questions? So these are, I guess, this is just some general analysis. I'll try to provide some intuition. Any questions?
So is that kind of taken as a definition for what a continuous phase transition is?
You could make it a definition.
What intuition should I have for the correlation length becoming infinity?
My next slide.
Next slide.
Yeah. Any other questions? So here, what I'm doing is that I'm just hiding all these like discussions of phase transition, blah, 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 into one simple notion, correlation length, right? That I can just talk, right? So let's build some intuition of what correlation length is. It's a very, very intuitive thing. Should I first say it in words? Let me first try to say it in words. Here's where we're going to get to, all right? I'm going to build towards this intuition. I want to study the physics of this table. How many atoms are there in this table? An insanely large number. Avogadro times God knows what. Do I need all of them? Do I need many body physics? Do I need to write down equations of motion of all these particles to solve for this? Not really. If I took half of the table and solve for half of the particles, I still get the right answer. All right. Means what? Means that the physics of this half is independent of the physics of this half. What if I take a quarter? I can still do it. How about I take small? How about I take small? How small is the smallest size that I can take the system and still get the right physics? What is that length scale? That's correlation. Correlation length is scaled because it's falling exponentially. Once you go 10 times the correlation length, the correlators have fallen by 10-fold. So you're basically, if you are trying to solve for those equations, you're doing this like you don't need to, right? When correlation length is, I don't know, 17, that's my favorite number today. 17 atoms, you have a 17 body problem. You cannot cut it down to a 2-body problem. You would be making mistakes. You would be missing correlators, physics. However, if your correlation length is 17 and you try to keep track of 11,000 things, someone can, yeah, you're just doing redundant calculations. Good. Now, let's just elaborate the word independent because it's absolutely crucial. When are two spins? Let's go back to Ising model. When are two spins uncorrelated? Go back to statistical. Sorry, what's it called? Probability theory. What are two independent random variables? Two random variables are independent in a state if the probability of S1, S2 is the probability of S1 times the probability of S2. That's what it means for them to be independent. So when I have a state, half of the table in some, I have a state where half of the atoms here in some probable, some position, some configuration, half of them are in this configuration. Instead of solving, finding the probability of all, like the probability of the whole thing, I can calculate the probability of this half and then this half and multiply them, and that would be a very good approximation of the probability of the whole thing. Okay? Connected correlators vanish, right? And that's the principle of clustering. You could have long-range correlations, right? You could have two spins that are 17 sites apart and they're still correlated. You could have short-range correlations, but no long-range correlations, right? So meaning that if you want to solve the problem, you could look at a block of 17 atoms. This block could be here, could be here, could be here, could be here, right? But if you have two of such blocks that are really far away, farther than 17 atoms, it doesn't matter. The physics of them could be just reproduced by simple multiplication because variables are independent. All right. Now, what did I tell you about? So imagine somebody hands you a physics problem. You start calculating the correlation length. You find that the correlation length is 17. All right, you have a laptop. You could run a 17 body problem on it, some sort of optimization problem. You can solve it. What if the correlation length is 17,000, 17 million? What if near continuous phase transition, your correlation length is infinite? What are you going to do now? So this was the problem that motivated in early 20th century that led to the discovery of field theory. What completely different angle, right? This is not high energy physics. But people were wondering, there are large class of systems that undergo continuous phase transitions. In these models, correlation length blows up, which means that there's no way of truncating the problem to small body problem. How are you going to solve it? Field theory was invented to solve this problem. In this limit, you can no longer treat the system as finite body. There are fluctuations at all scales. I repeat this. One key element of field theory is that you're dealing with a system that has fluctuations at all scales, long range, arbitrary range scales, right? Now, here, hopefully, now this statement makes sense. Field theory is not a 4-body problem, 5-body problem, 17-body problem. It's intrinsically many body, all bodies at the same time, all particles at the same time. It's a theory that specializes to that. It's a theory that's invented to deal with such a situation. Does anyone have a guess of how on earth are we gonna solve an infinite body problem? How is field theory gonna save us? From things you've learned. I mean, I turn the problem into probability, right? How are we gonna? There's a very deep intuition that this is happening. Yeah.
Consider your infinite bodies all part of one continuous thing over space.
Yeah. You guys have all taken thermodynamics. You have already learned this, seen that this works in. You're completely on the right track. So here, the idea, well, let's first build towards it. If, yeah, okay. When you have a material, right, that has an Avogadro number of particles, right, and you want to describe, you want to solve for the system, but not for absolute gory detail position of each particle of a gas of atom. What you care about is some sort of a coarse-grained average observable. You don't care about the probability of this particular configuration. You don't care about this probability. You care about the probability of if you take a box with a gazillion number of atoms in here, how many, if you add up or average them, what is that average going to be? Right? So this state, from this average point of view, is equivalent to this state. Oops, sorry. Is equivalent to this state. You won't be able to distinguish between these. Right? What is pressure? When you have a gas atoms, you don't care for the position of all atoms. That's a hopeless problem. But when you talk about pressure, it's basically the quantity is some sort of averaged measure of the momentum that's transferred to a wall, summed over all the particles that are hidden. So you already know that there's some static intuition that says that when, for example, in Ising model, if you talk about only the magnetization, which is the total, these are little magnets, magnetization is the total sum of them, sum of the total magnetization. If you care about the total magnetization, you already know that you've learned in StatMech or thermodynamics that this coarse grain degree of freedom, that I'm going to call average coarse grain of macro observable. This you could build a theory of, you could solve for without the knowledge of short distance physics. This only occurs if the short distance fluctuations are tame. I'm going to try to provide intuition for what that means, the short distance fluctuations are tame. By the way, this has another name in physics. Can anyone say it? Is the principle clear? Engineers, and not me, but the mechanical engineering department, these guys build bridges. Have they solved for the physics of like gluons inside the proton? No. How can they build bridges? How could they build a predictive theory and like predict everything about it? Somehow, for building a bridge, they use F equal ma, and F equal ma doesn't give a damn about interactions of gluons. Right? You don't need to know about that with microscopic methods. You don't need to know about the microscopic correlations of gluons inside the proton for building a bridge because it doesn't matter. Or a better term, technical term, is irrelevant. That's a technical physics term. We'll use that a lot in this course. So there's a hypothesis. There's a belief, it's like a faith, that physics at very, very short distances is irrelevant for macroscopic coarse-grained observables. Let's call that the hypothesis of renormalizability. All right? It just means that that's what I meant by saying short distance correlations are tame. Tame means that they're not so bad that you cannot build that effective theory. Can you come up with a setup? Well, think about this. Are there examples of physical problems, classical physics problems, where short distance fluctuations, well, destroy your coarse-grained observables? This is there are such examples. I don't want to make a comment on when we're recording. We'll do that afterwards. But remind me. All right. We could not solve or observe short-range correlations, right? We cannot observe them. So the correlations of macro observables are what we're going to observe. The hypothesis that the correlators of macro observables are independent of short-range correlators. This occurs if the short-range correlations are tamed enough or otherwise irrelevant. F equal ma holds independent of the microscopic state of atoms. All right. Good. Nah, I cannot help it. I'm going to put you guys together. Do you have a problem in mind where it's classical physics, but we cannot predict coarse-grained observables? What's a problem that's like that bothers you a lot in your day-to-day life as well? At least it bothers me. The correlations may not be in space. It could be in time. What's the example? What's the one thing we could land stuff on the moon, but we fail to do a simple some classical calculation. Exactly. Why is that? Because sometimes when it comes to weather forecasts, the equations are such that the butterfly effect, flipping, tiny change in the short range correlations, some small detail that occurs locally at some moment in time can totally screw up long-term correlation. Now, here, be careful. This is not quite that example. Because a short range, the fair comparison would be some butterfly like flying somewhere in Brazil, being a short range perturbation, that cannot screw up the average temperature of West Lafayette averaged over 10 years. That is a real coarse grain observable. However, there are some observables in this setup that are highly sensitive to that fine detail, right? Good. So in classical physics, you're not guaranteed that there's always a nice, we call it also separation of scales, short range versus long range, right? They're not always guaranteed. All right. Let me see how many more slides I have. 22. All right, good. I'm getting there. I'm going to pause for questions because what I'm going to do in the remaining 15 minutes is going to be very, very crucial. I want to change your perspective. I want you guys to reset. Any questions about this? So the key word here is coarse grain observables, right? So what I'm going to discuss here is how renormalizability, or at this point, it's just a set of words, right? Separation of scales, short range being irrelevant for coarse grain observable. I'm going to discuss that in the context of one simple model that you're very familiar with, Ising model. I'm going to go through it real fast, but it's going to be a homework problem for you to work at it, right? All right, what is it? It's the Ising model that I talked about in 1+1 step. One space image. All right, what is the coarse grain observable? And as we're going to do this, at the same time, I'm going to explain what the continuum limit is. All right, that's the tricky part of it. So that's why you have to do the homework on the side. It's going to be super quick. So I told you that I have an Ising model. Imagine I tune this in 1D or whatever dimensions it is. It's not the 1D is not a good example because it doesn't have the properties that I want, but it doesn't matter. Imagine I tune the system near continuous phase transition. So I put the system at finite temperature, and I happen to be sitting at temperature near the critical temperature where the correlation length is in there. All right. So what am I going to do? I'm going to introduce an observable called magnetization, which is I draw a box of n adjacent spins, and I'm going to average them. First thing that you notice is that while spin was either up or down, the average could be any number between 1 and -1. As n becomes larger and larger, it could become a continuous variable. So magnetization, now I'm going to call this X, right? So this is a position, right? Like I'm doing, so there's this, I'm coarse graining my lattice if you wish, right? So I have a lattice and I just coarse grain. I click this box, and this box, and this box, and this box, and in various steps I coarse grain. So my magnetization, I'm going to keep doing this, right? Both position and magnetization become continuous degrees of freedom. I get something that looks like a field. Good. Here comes the calculation. So what am I going to do? I'm going to do this very quickly. But if you do this, you're going to get scale amount of it. First thing I'm going to do, I'm going to use a trick. So what was Ising model? Ising model has a discrete configurations for SIs, right? And then you have the probability of a configuration like this, E2 minus beta H of SI, right? That's what it is. What I can do is this. I can say, just at the level of the Ising model, I'm going to write an equivalent formulation. I'm going to say, replace your SI with either plus 1 or minus 1. Replace this by a continuous degree of freedom between minus 1 and 1, right? Call that phi. All right? But I'm going to force it to be either plus 1 or minus 1. How? So first I'm going to, well, this way. I'm going to multiply the probability by e to minus g, some constant, phi I squared minus 1 squared. When g goes to infinity, this variable takes either plus 1 or minus 1. Right? Good? All right. Epsilon is my lattice site. So S of I, Si plus 1, I can write it as S of x plus epsilon. That's my Hamiltonian. Good. Subtract from it a constant. Subtracting constant from Hamiltonian shouldn't matter, right? Now, if you take this expression, just massage it, you can write it as a second as this expression. So this is half j sum over x, sx plus epsilon minus sx squared. As epsilon goes to 0, what is this? So you replace s with phi. This becomes derivative of phi times epsilon. So the Hamiltonian becomes j over 2 del x phi squared. It looks like a kinetic term for a continuous field. X is a spatial derivative. There's no timing, right?
No terror is a
It's not kinetic, sorry, something like that. It's this term. We call it kinetic term. It's part of the kinetic term in the field theory. But it's this term. As this step was very quick, but you're going to fill in the gaps for yourself later. But is it clear what I'm doing? First, I replaced SI with a continuous variable, but keeping G large. But we're going to, in the next step, we're going to quickly do the coarse graining, and you see that how it naturally pops out. But I just wanted to tell you that using this trick, you can get a clear action as captured. Remember this. I have a bunch of questions for you to think about at the end of this lecture. This step is crucial for answering some of this. What I want you to think about is that why did a Gaussian come up? This is a Gaussian, right? All right. Good. So, remaining 5 minutes, what am I going to say? I'm just going to coarse grain. I start with a partition function of the fine temperature Ising model. First, I'm going to do the following. I'm going to say, so I have some sort of a, let's say, configuration that looks like this. I don't know, something, right? I'm going to draw a box here, draw a box here, draw a box here, and replace these S's by their magnetization. Good. Now, what I had is I had a sum over all configurations. I can write down, this is a precise thing, I can write down the sum over all configurations as the sum over all configurations for M magnetization, with the next sum, which is summed over all microstates that contribute to macros. Let me clarify. This, having a fixed M, is a macrostate. Another example, let me just do an example. Let me do quartz graining for 3 of them. Right? So how many microstates do I have? 8 microstates. When I do averaging, let's just say I sum, right? How many states do I have? I can have -1 or 1, right? I have 2 states. So here I have 3 degrees of freedom. I replace them with a single macro. So this was a micro state. This being up or down is a macro state. Each macro state has microstates corresponding to it. If the sum to 1, this is 1 state, microstate, this is another microstate, this is a different. This is a summed over spin. Right? These are microstates that correspond to a macro state. Everybody follows? So I can write down my partition function, sum over all microstates as a sum over macrostates, and another sum, which is over all microstates that contribute to a macrostate. This is like the temperature of the, this is like a particular pressure or some sort of macro observable, and these are all the microstates that contribute. Now, imagine I'm powerful enough to do this sum, this second sum, explicitly. So what do I obtain? I obtain a generating function for my macro correlators. This has a name. This is called free energy. Right? Is it clear? This is an exact step.
What term is called the free energy?
I'm calling this FM. That's free energy. Yeah, if that comment was quick, ignore it. But that's just a sum. All right? Everybody's with me? It's an exact step. Good. So as you keep doing this, you can keep doing this like many infinite number of times. First of all, this sum over macro thing become continuous variables. So you will have to, and then here what you end up with, your functional, becomes, instead of a function, becomes a functional of a continuous field configuration in space. This sum becomes a path integral. This is how we're going to land on field theory. All right? So as the lattice spacing becomes very small, m of x becomes a continuous function, and we're summing over all functions m of x. This is a functional integral. This is a schematic way of writing it, and this is the weight associated with it. The space of configuration is the space of all functions m of x, aka magnetizations in space. All right? Okay, so here it is. The summary of it. The continuum limit is what you find when the correlation length goes to infinity. Correlation length over the lattice spacing. Dimensionless correlation length goes to infinity. Only dimensionless things can go to infinity. Right? The number of particles within one correlation length is large. That's what it means. Then field theory kicks in. That's what the regime of statistical field theory. Low energy excitations of this theory can emerge that are different from high energy particles. We're going to call them quasi-particles. They can be pair created, annihilated, blah, 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 and then field theory will capture that. It's the promise of where we're going. Finally, the last slide for you to remember. Key ingredients of field theory. Fluctuations. Today it was thermal fluctuations. Next lecture will be quantum fluctuations. All right? Not just fluctuations, but fluctuations at all scales. All right? Locality. Well, we're going to talk about action principle. But here was that action, the Hamiltonian I wrote was local. That was essential. Symmetry. Symmetry played an incredible role. You didn't see it. I was hiding it. But it played an important role. Finally, normalizability. Short range correlations are tame or irrelevant. These are the principles and the ingredients that you need for field theory. If it's thermal fluctuations, it will be statistical field theory. If it's quantum fluctuations, it will be quantum field theory. Same formalism, same exact formalism. They're related. All right, questions. I'm gonna pause for questions and then show a set of questions for you guys to think about. Questions?
I guess a question about mathematics that you did before, like, have we shown that f of m exists?
Oh, I just sum. Let's say somebody is very powerful, can do the sum. And I'm gonna call that sum, whatever it is, take the log of it, with a
Okay.
minus 1 over b, I call that f.
Okay, sure.
Someone very powerful can do that. In your example, that powerful person, in your homework, you're gonna be the powerful person. All right. Question to think about. This is for you. What is a quasi-particle? I just poked you. I did not give you a definition or anything. How is it different from a fundamental particle? Or said differently, what the heck is a fundamental particle? Does the existence of quasi-particles imply that fields are somehow more fundamental than particles? Are there field theories that have no particles? And finally, no, not finally, one before finally, starting from field theory, how do you define a particle? We're going to have a lecture on this specifically. What is a particle? But I want you to start thinking about it already. There are many answers to this, actually. Is there a connection between the, oh, this is a fun one. Is there a connection between the law of large numbers, the central limit theorem, and field theory? The answer to these are very important, especially this is like when they say they discovered Higgs particle in lab. What exactly do they mean? When they saw the Higgs particle, what the heck did they see that they say declared discovery of a particle? And this is for you guys to think about. All right, thank you so much. Again, so I have no idea what your background is, guys, because it's a semester. This semester is different from